Hi, my name is Nagela, and this is my Lab 4 presentation on oscillations. The objective of this lab was to observe and quantify the motion of a mass oscillating as it swung from a spring in an arc, construct a computational model using Newton's second law to fit the data, compare the predicted and observed positions of the mass over time, and see if the system satisfied the energy principle. The video of the motion was provided, so I recorded the position data in Tracker and started my analysis from there. After doing this, I calculated the spring stiffness constant and an original length of the spring. From here, I created multiple models in VPython using Newton's second law to predict the motion of the mass, using the assumption that the net force consisted solely of the force of gravity and the force due to the spring, and then compared the observed and predicted positions to find that the model was accurate based on the oscillations. The predictions of the motion of the mass followed the pattern from the data received from analyzing the video. However, the model became less accurate as time increased, indicating that there is another force acting on the mass, slowing it down. It's important to understand the fundamental principles behind this lab. We start with Newton's second law. As stated in the previous labs, Newton's second law takes mass, velocity, and change in time and produces a net force that causes the object's motion. In this lab, the mass of the spring system was 0.402 kilograms, with a zero vector as the initial vector, a position in the third quadrant of the coordinate axis. Applying this to my VPython code, the initial positions and velocity, as well as the mass of the ball and the starting time are accounted for. These lines of code are found in the while loop because they constantly update the position of the spring with increasing time. So here we see Fnet being referred to. You may be wondering, how exactly do we find Fnet? Well, the first force acting on our system is the spring force, calculated by multiplying K sub S by the stretched length in the direction L hat that restores the spring to its original state. Applying this to the VPython code, you can see that Earth's gravitational constant G, the calculated spring constant, and L naught. This part of the code also calculates the change in length of the spring throughout its motion. S, or L minus L naught, changes constantly, so we cannot simply plug in a single value. In the while loop, we calculate the spring force given this expression. The second force acting on the system is the force Earth exerts, the gravitational force. This force is calculated by multiplying the mass of the system by the gravitational constant G in the negative y direction. Here it's shown in code form. Now that all the forces have been calculated, we can place them into an updated code with net force included. The net force is equal to the spring and gravitational forces combined. The second fundamental equation included in our code is the energy principle. It states that the total change in energy is equal to the change in kinetic energy plus the change in potential energy. Based on our system, the mass, the total change in energy is equal to zero since what is in our surroundings is negligible, or zero. All of these values can be calculated given these equations. Adding this to our code, we see the equations rewritten in VPython with each of the initial energies defined as well. The energy changes are calculated in the while loop because the energy of the system changes as the position and velocity of the spring mass system changes. These changes are plotted into the VPython program created. So the blue line represents the oscillating kinetic energy with time. The red line represents the oscillating spring potential energy with time. The green line represents the oscillating gravitational potential energy with time. And the yellow line represents the sum of all the energies combined. So the yellow line is at the zero line. So we'll just go ahead and let this run until it's finished. Here's the analyzed video. After calibrating the length scale and choosing my coordinate axis, I started tracking the position 4 frames into the video clip until the end. You can see the graph to the right shows the oscillating sinusoidal motion of the spring. From here, I exported the position to a CSV file, which was then imported into my code. Given all of this information now, we can run the code to give a visual representation of the predicted motion that VPython calculates versus the observed motion that we analyzed in Tracker. When we run the code, we see that the red observed motion and blue the predicted motion lines are similar, showing that the fundamental physics demonstrated earlier can be used to predict the motion of an oscillating object. So we'll just go ahead and let this finish as well. The discrepancies between the two, which we can see, are most likely due to the error when tracking the video. What does it mean? Is the energy principle satisfied? If you recall this visual representation of the model, we see that even though change in kinetic energy, change in the potential spring energy, and the change in the gravitational potential energy all oscillate, the total energy, the yellow line, is a straight line at zero, meaning that the sum of all the energies equals zero, satisfying this principle. What does it mean? Here we are asked to compare the oscillation periods using x and y positions. A period is simply the time it takes to complete one cycle. or from crest to crest or trough to trough. I simply took the last time measurement, which corresponded with the x or y position, and divided it by 5 to get the period. The reason for the 0.133 difference between the two periods could be the gravity's effect on the motion in the y direction. In the x position, the spring force acts on the motion. In the y position, both the spring force and the gravitational force act on it. Therefore, it will take longer for the x position to return to the initial point because there's a weaker net force acting upon it. So here's a quick recap. We used Newton's second law and the energy principle. We made conclusions about how well the energy principle predicted the motion of the oscillating object, and we ultimately found the period of the object and the x and y positions. Thank you very much.